All right, so this is my trail board that I put together from spare parts. Separate video on this, but just to run it down, it's an 18S2P P45B pack in the rear. It's made from a mixed batch of cells, which I don't do for like customer batteries, but rather than just let them sit, piecemeal in the case, made a pack out of them. And so Cannon core was broken, fixed it, changed the plug over to regular bullet connectors and ran it into the front. Either way, this has some use on it, and we're going to take a look at the battery spread, and we're looking at it first because we are at nominal voltage, which means we are just at about half, maybe a little bit over. And it's hard to see in the sun, but that's just at about half. If we look at our battery spread on VESC tool, we will see the cells are damn near even. Sit down and talk. So the cells are damn near even, and this is because, especially with relatively new packs or packs that are in good condition, at nominal voltage you will usually see the least amount of spread, the most amount of balance, and the most close numbers. So the plan for this segment is to start here at nominal, and then I'm going to take it down to essentially empty, and then a little bit beyond that, and then charge it back to full. And at each of those stages, I will explain to you what the effect of either good balance or bad balance would have on your overall use and experience of the device and its battery. So again, starting at nominal, which is just at about half, maybe a little over, a little under, but more or less at around 3.6 volts per cell. So here it's fairly even, and we're going to drain it down to empty, and then we're going to talk about what effects balancing would have near empty. Before moving on to the rest of the video, there are a couple of points to clarify. This mostly applies to custom or DIY VESC one-wheels and most high-performance e-skates with a charge-only BMS unit. This does not apply to future motion one-wheels like the XR or the GTS series, and it does not apply to the float wheel ADV. The reason for that is because most custom-built VESC one-wheels, the power into the motor controller is direct and can't be physically cut off by the BMS if it detects a fault. In a board like this, faults can be reported to the VESC to signal if there is a problem, but it won't just drop the rider or turn the VESC off entirely, at least if it's configured properly. As far as future motion one-wheels go, they have their own BMS architecture with their own firmware, so it's really just best to do whatever they tell you with their batteries and chargers. That's essentially all you can do anyway if you care about your warranty and service availability from the OEM. As far as the float wheel ADV goes, the BMS does manage discharge into the motor controller and can indeed shut off the whole board if there is a BMS fault. For some more information on that, you can see my float wheel ADV review linked to in the description below. That being said, some of these things do apply more broadly to PEVs, batteries, lithium-ion battery packs, etc., and so some of the demonstrations in this video can be useful in that application, but I did want to clarify what I'm really focusing on for this particular explanation. Okie dokie, artichoke. We are now at an empty battery, so same board, different motor, but it's the same charge. And we are now at what most would consider empty. Battery is at about 3.0-ish volts per cell. I'm already in the low voltage tilt back area, so if I do ride this, it will start tilting back to signal that the battery is empty, and the LED is indicating 1, which means that this is essentially an empty battery and needs to be recharged. So if you're familiar with any of the prior videos I did on setting up VESC one wheels, 3 volts per cell is empty regular. That's what I consider it, empty regular. It's not empty empty. Empty empty is 2.5 volts per cell. Now, it is safe and within manufacturer spec to take your battery down to 2.5 volts per cell. Most people don't, and you'll probably end up with a longer cycle life if you just discharge down to 3 volts. That being said, you'll notice that at least as far as the data readout is showing us, it does look like the balance is not super great at the bottom, even though near nominal, it was dead on even. And this is the kind of spread that may bother some people, but you'll see why in a moment, why this kind of spread at the bottom or at the top Might not be as bad as it looks. And, you know, this isn't actually all that bad, to be honest. And what we're going to do is I got my limited edition Bodie Harrison Float Life bonk block here, which pretty much just sits on the shelf unused because it's a collectible. And I'm going to use it to just stall the motor, which you should never do. Never stall the motor. That's a bad idea. But I'm going to do that just to put a larger load on the battery so I can draw as much current as I reasonably could without, you know, going out and doing it on an active ride. And what that's going to do is it's going to pull the cells down below 3 volts. Some of them are going to hit 2.5, some might hit that below it, and that wouldn't be a voltage range that would necessarily be bad in the moment, because you're going to see a dynamic load. You're going to see a dynamic voltage set, not an at-rest voltage set. And then you're going to see the cells settle. Now, no one would actually ride past this point. So even with an uneven spread, if you're hitting this point, you've achieved the end of your charge. So even if you did want to ride down to 2.7 volts per cell, you wouldn't get much out of it because the energy down there is not very great, and the battery would then start to sag under load and reach your low voltage cutoff anyway. So you can just see as we place a load on the motor from stalling it out, which again you shouldn't do, we are now dropping below 2.5, and now I can actually feel the nose start to drop out a little bit and hiccup. This is bad. Don't ever do this. But you'll see that if I let off, voltages rise back up, and now they're well above 2.5 volts per cell, and the voltage starts to settle. So any voltages you saw that went down to 2.4, 2.3, 2.5-ish, those are not actual voltages. That's just what they are under load. Much like when you open up a spigot or a faucet, the pressure behind the valve drops as the water flows. Similarly, the current flows and the electrical pressure, the voltage, begins to drop. But at rest, it then starts to settle. So here I am now with 0 lights, so this is dead. I mean, it's still on, but the battery meter is like you have got nothing left. But we're still at about 2.8, 2.9. So if these cells were even less balanced, if some were at 2.9 and some were at 2.7, which is, you know, a little bit of an imbalance. You might see that on an older or worn pack. As long as they're being discharged evenly and none are sticking out to drop all the way down and completely bottom out, which would be a sign of damaged cells, bad welds, whatever, as long as they're discharging evenly, this is still going to deliver all the energy that I expected to until the device tells me that the battery's empty. Because the devices that we're riding, specifically onewheels and e-skates and VESC-based onewheels, they're all signaling you to recharge at a voltage where most, if not all the cells, are at 3.0 volts. If some are at 2.8, that's still above empty, and that's fine. If some are at 2.9 and some are at 3.1, that's not great. That's not probably very good, but the signal for empty battery, as far as your experience and what the device is delivering, happens well before we get to this point. So we've drained some more energy at about 2.9. We can do it again, because the board still has energy in it. If I ride over here, it's going to tell me to, yep, there's that tilt back. It's going to tell me to get the hell off. We're going to go back to our limited edition Bodie bonk block, stall the motor again, which again is bad, and we're going to push the cells a bit down lower. Again, don't do this, but you're seeing 2.3, 2.4, 2.5. I'm feeling the board getting really upset at me. And you start to see a massive spread. And the reason you see a massive spread down at the bottom is because the variances in capacity per cell, per parallel group, are most magnified at the bottom, where you simply don't have a lot of energy left. That's just a characteristic of electrochemical energy being stored in cells, is that when you've depleted them, there's not enough left and the variances reveal themselves. That's natural. It's happening with cells that are perfectly matched It happens with cells that are made on the exact same date with the exact same batch code. Because it's electrochemical energy, there's always going to be variation. It's also why, we're going to charge this board back up, you're going to see similar variation all the way at the top of the charge. So 4.19, 4.20 volts per cell, you're going to see that exact same kind of variance. Usually you don't with a brand new, good condition, fresh battery, but even so, when we get to full charge, I'm going to explain why that lack of true OCD balance is not going to really affect how the pack behaves. So here we are at the bottom, and you see our resting voltage is still at 2.8, which still technically is not empty. We're still within the realm of empty regular. So I could just do this again, which again, you shouldn't do. Never stall your motor on a VESC one wheel. I saw at least one cell go down to 2.1. That was not a good idea. So don't do that. That's stupid. But here we are again, bounced back up, 2.7, 2.8 volts per cell. And so our resting voltage will increase even more. If I shut this off, come back 5 minutes later and turn it back on, I'm probably going to see about 3 volts per cell. Ooh, isn't this pretty? Anyway, we're nearing full charge on the board. As you can see, it is currently charging. And if you look at the third little data point down, you will notice that I in is currently fluttering at about 1.5 amps. This is a 6 amp charge. It's been at 6 amps the entire time. And the current is going down because it is in the constant voltage phase, which means it is no longer a constant current. It is now applying the full charge voltage as the current tapers off. So that's what it's doing now. So we're near the top of the charge. If the charger were to be disconnected while there's still a few amps flowing, the voltages would drop. And that would be kind of funny, because then you would not actually have a full charge. But if you actually take a look, so we're still just sitting here plugged in. If you take a look, you might notice a couple of interesting things, specifically cell or group number 13. It is lagging behind the other ones. And when this battery was empty, resting voltage, more or less, cell 13 was actually higher. So what does that mean? I don't know. However, it does charge and discharge at the same rate as all the other cells, even if the actual full level is not exactly as high as the other ones. You'll also notice that in this particular thing, now this board has an X-Lite V4 in it, and the orange blips you're seeing are the channels being bled off. So we're actually at a point where the BMS is balancing the pack off. And just to briefly describe it, once the BMS reaches the threshold that is set in the settings, which you can alter, but you should probably just leave them alone. Once it reaches those conditions, it will then periodically, once every few seconds, turn on a channel where it bleeds off energy through a resistor in order to reduce the energy in the cell. So that is generally what passive balancing is. Most of the BMS is used in these types of devices, same as would be used in an E-skate like the one up there. Most of them are passive balancing in that they bleed off energy in order to bring that cell group down while the other ones are being charged up. That is generally how balancing works in these types of devices. Nothing to say of active balancers, which are different. However, so even though all these groups are being bled off, because there's apparently more of a spread than this thing is okay with, what is going to happen is that most, if not all, of these cells are going to end up with a resting voltage of somewhere between 4.19 and 4.21, 4.22-ish volts, which is full. And despite what some might say or feel, the difference between 4.20 and 4.19 is not really going to impact the end use experience of the device. The only time where voltage fluctuations and differences and a lack of balance is going to impact the user experience of the device is when either those voltages go out of the normal safe operating range, which is from 4.20-ish full to 2.5-ish empty. If it's outside of those, higher than 4.25, below 2.5 resting voltage, that will damage the cell. That's bad. If the full charge at rest for half of these cells is 4.22 and the other half of them is 4.19, you're unlikely to notice an actual difference. The reason I'm able to say that is because if you watch the cells, and if you do this enough, you'll find that the amount of energy you get from going to 4.19 resting voltage to 4.22 or whatever, in the case of this at least, equates to maybe like 20 feet worth of riding, if any, because once you activate the motor and you put a load on the battery, they all start to drop. If you get off of it, you'll notice that those few hundredths of a volt that you worked really, really hard to get are immediately gone, because that's just how the discharge curves work for most cylindrical lithium-ion cell, which is what you use in these boards. So this thing is going to try to balance the battery in here until it reaches the threshold that it sees as acceptable, which is a delta or a spread of 20 millivolts, which is a pretty tight balance, in my opinion. And that's about it. This top balances, as most BMSs with a balance function do, which means it balances near the top of the charge. And once it passes a threshold, 4 volts per cell, 4.1 in this case, that's when it'll allow the channels to turn on to bleed off. Now, again, this is all talking about a pack that is functioning properly, but may or may not be the most perfectly balanced pack in existence. And I'm using this as an example because this board was made from spare parts and scraps. The cells in that pack were pulled from different batch codes, and I always have some left over because when I make packs for customers or other people, I don't like to mix batches because I just don't want to. I like a uniform batch code for every single pack, but I'm always left with some incidentals here and there. So I collected them, built them into a pack, and so it is not the most uniform spread. However, in practice, this, which still is a healthy, normally functioning pack, because no cell drops faster than the others, no cell charges faster than the others, so they're all working properly, and at no point do any of those things stray outside of their safe operating range. With that being the case, the delivered energy, and in the case of a device like this, the delivered range, is essentially, in effect, unaffected by a spread of 50 millivolts, 60 millivolts, especially since these things only discharge down to 3 volts per cell, and you're not dipping in to that last half a volt where most capacity differences are felt. You're just not going to be delivered the kind of impacts that most might think if a pack is not perfectly balanced. And again, to clarify, that's assuming the pack is working properly, staying within normal safe ranges, and the balance is not so bad. There are cases where a cell group can be a half a volt off from the others, at which point that's, in my opinion, a problematic battery. But that's not what I'm talking about in this video. That's a different topic when you're looking at a battery pack and through how it behaves dynamically, trying to find issues, which is not what we're doing here. So in an effort to conclude this video and not drag it on too much longer, by the way, this is a completely different board, but still with an X-Lite V4 in it and a similar battery configuration. So again, to conclude this video, if there are any other questions, I will do my best to answer them. So feel free to leave a comment below. And the goal was to sort of clarify and demonstrate what battery balancing and what a balanced battery looks like and what it does, and what that actually means for most cases of devices like this. It's quite often that the word balance and the idea of balanced batteries and all that stuff is used as marketing fluff to sell products and services and whatever. And for the vast majority of it, it's just nonsense. It's meaningless, and it is frustrating because it's kind of low to leverage scientific illiteracy and misunderstanding to further a product that may or may not be any better or worse than any other. And so my hope is that in showing a more visual, practical demonstration of what battery balance is in this context, that it could be helpful for making more discerning choices and things like that when it comes to the purchases that any given consumer makes in this hobby with their project. And so if I did get something wrong, at least blatantly, please feel free to correct me in the comments as well. And as always, I appreciate your viewership and your time. Thank you. Take care of yourselves.